second lecture of NoSQL playlist. In this video, we'll be discussing the important topics or must-cover topics from second module. If you're new to my channel, do check out the NoSQL playlist where I have every module, and along with that, even the important questions have been uploaded. So do check that out and subscribe to my channel so that you don't miss out any of the further updates. So let's get started. So in second module, there are three chapters. So the first chapter among that is distribution model. Okay, under distribution model also there are 5 topics. So they are very easy ones. So let's get started. So the first topic is we'll understand what distribution model is. Okay, so we know that NoSQL database will have large amount of data, large volumes of data and traffic is being generated, right? So it is very important to handle this large data carefully so that the contents of the data are not misplaced or they are not missed. So in order to do that, this data would be arranged in form of clusters of servers. And in order to handle these clusters of servers, in order to distribute the database into these clusters, we make use of distribution models. So there are two important techniques which are used for distributing the data across multiple nodes. One is the replication, other one is sharding. So these two models will help in balancing the workloads, and if you are balancing how the data is being distributed, thereby even the performance would be improved, right? But then along with that also comes challenges like consistency and all the other things. We'll be discussing it further. So the first among this is single server. Single server is the simplest distribution model which is present in NoSQL database. So the entire data you're distributing it to a single machine. Right. So here the distribution model is made to run a NoSQL database on a single machine. So in this setup, all data is stored and processed over one server. So when you're storing everything in over a one server, then there is no complexity only, right? So that is, I don't have to manage multiple nodes here because everything is being concatenated to just one node here. So it is beneficial because it eliminates the operational complexities of maintaining a distributed system. So when you have distributed system, multiple clusters would be there, and maintaining all these clusters would become a major task. But then when you're talking about single server, there is only one server, so it is very easy to maintain this, right? So it is very easy to understand the environment for developers. Again, so when we have a simple storage structure, it becomes very easy for the developers also to understand. Then it is better suited for small or simpler applications. So it is better suited for simpler applications where you're just making use of a simple database and you're storing it. Graph database is they are used for single server configurations because they can take full advantage of their native data models. So along with these advantages, single server configurations can limit the scalability. That is, only specific amount of data can be stored. But then if the data volumes are increasing, then it becomes difficult, right? So in such conditions, we have to look for other other alternatives like sharding or replication. So we have sharding here. Sharding is a technique where the data is partitioned into small pieces. So you take a large chunk of data and then you are dividing it into small pieces. So these small pieces are called as shards, and these shards are distributed across multiple servers. So the main goal here is to improve the horizontal scalability. That is, you're distributing the load equally among multiple servers here, right? So here each shard is responsible for a subset of data because each shard will have some content of data. This entire data is being divided into different shards, right? So each shard will have a subset of data which it has to handle, right? So by distributing these shards across different nodes, the load is spread out. So as I told, the load is evenly distributed, thereby enabling the database to handle greater volumes of traffic. So what are the key points of sharding? First one is balancing the load, right? So ideally each shard should be evenly distributed across nodes to ensure that they are evenly distributed and there is no overloading happening. Then we have aggregation, right? So aggregates means group of related data. That is, in sharding, aggregate should happen, and ideally the same data should be present in the same shard. Thereby we can improve the read performance. For example, all user data for the customers in Boston must be stored in the same data center, right? So that is about aggregation. And next we have clustering. So shards should group the data that is often accessed together. That is, grouping data that is usually accessed together. So by this way we are minimizing the need to access multiple nodes. So instead of accessing multiple nodes, when the contact information is stored into one shard, all these entire things are stored into one shard, it becomes easy to access this shard completely, right? Next we have is rebalancing. That is, over time certain shards may not be utilized, right? They may be just stored. In such conditions, we have to perform rebalancing here. That is, from the most popular shards, we have to distribute the load equally. By rebalancing, we are reducing the complexity also. So sharding can improve read and write performance. However, it could lead to resilience issues, because if a node fails in the shard, then the data cannot be accessed unless and until I replace this, or I I restore this, or reallocate this, right? So these are a few key points about sharding. So next, here we have figure 4.1, which is how the sharding works. So the data is divided into smaller units. So this data is being divided into one unit here and one unit here. So these units are called as shards. So here each shard is stored on a separate server, right? So there are multiple servers here which are being accessed. So here each node will be responsible for handling its own subset of read and write requests. Next, we have what are the challenges which we face during sharding. So first one is data distribution. So here we have to ensure that data is evenly distributed among the nodes. So even distribution should happen. That is one of the initial challenges. Then we have application complexity. That is, sharding requires changes to the application code in order to handle how the queries are distributed across shards. That is, changing application code to handle how queries are accessed across the shards can again lead up to a challenge. Then we have rebalancing. That is, as the data grows, we have to reorganize it, and then splitting of data is also necessary. And by doing so, we can reduce the load, reduce the downtime, right? Reduce the overtime, right? So rebalancing is again a very important aspect. Next we have is master slave. So master slave is a simple technique where one node is master, other node is slave. So we know master slave will perform all the write operations, and these writes are propagated through the slave nodes. Master node will have write operation which is propagated to slave node, and slave nodes are only capable of handling the read operations. So read operations will allow us to scale the reads horizontally. What are the advantages? So first advantage is read scalability. That is, by adding more slave nodes, the system can handle more read traffic, right? So there is master here, which is having the write operation, and if there are multiple nodes, so multiple nodes could read the data efficiently, thereby increasing the scalability. Then we have read resilience. Read resilience means if the master node fails, then the slaves can still serve a read request, and thereby it will improve the availability aspect. Speaking about the limitations, the first limitation is write bottleneck. That is, since all write nodes must go through the master, it becomes a bottleneck for writing heavy applications. So again, as I told, if master node fails here, then it becomes difficult for execution of the slave nodes, and along with that, for each time for the read operation to happen, it has to come from master only, right? So thereby master becomes a bottleneck while performing the write heavy applications. Next we have is master failure. That is, if a master fails, write operations will be halted until a new master is selected. So these are the limitations. Advantages are very simple. Next we have replication can also introduce consistency challenges, like especially in read heavy systems. Like clients reading from different slaves might see the outdated data because of the time it takes for changes to propagate from master to slaves. So here they have spoken about the consistency issue, where one master has performed a change, and till the time it reaches the slave, one master has performed the write operation, and till the time it reaches the slave, another master has again performed a change over the same data, and this change is quicker than this change. At that time there will be a consistency issue, right? So this replication can also introduce consistency challenges in master slave orientation. Okay, so here we have the figure which speaks about the master slave diagram. So here master node will handle all the write operations, and the slave node will replicate the data from master, and it will serve the read request. So here it will allow the improved read scalability, right? So this is a simple figure for a master and slave replication. Next we have is peer-to-peer. Peer-to-peer is again a very easy topic. So peer-to-peer means there is no master here, no designated master. So here all nodes are equal and each node can handle both read operation and it can do write operation also. So peer-to-peer replication will provide better resilience and scalability because there is no single point of failure. Right. So if you see this figure, it's about peer-to-peer replication that has all nodes applying read and write operation to the data. Right. If one node fails here, other node in the cluster can continue to operate. Right. This will ensure that the data remains accessible. If this node fails also, the data could be accessed through this way if this connection fails. Right. So that is one of the advantages of peer-to-peer connection. So looking at the advantages, the first one is fault equal weight across nodes. That is, equally weights are distributed across nodes and they are equally accessible to each other also in peer-to-peer connection. Next we have is fault to tolerance. So if one node will go down, then other nodes can still serve both read and write. Thereby it will increase the availability and resilience aspect. Next we have is write scalability. That is, multiple nodes can handle write. Right. Thereby it will reduce the bottlenecks which will occur because of only one master. So if this master is taking a lot of time or this master is not generating the write quickly, then I can go with the other master, right? So thereby write operation scalability is supported here. Next we have challenges. So under that we have consistency. So under consistency we will come across the write conflict. That is, if any node can accept write, there's a potential for write conflict. Like for example, if two nodes are trying to update the same data at same time, then it can lead to write conflict. Next we have conflict resolution. That is, some systems may implement mechanisms like quorum writes or conflict resolution strategies to handle inconsistencies, but then it will again lead to increased in complexity. So it is very important to look at the trade-offs between the availability and consistency here. We can increase the availability, but we have to tolerate some level of inconsistency when it comes to peer-to-peer combination. Next, we have combining sharding and replication. So in practice, sharding and replication are often combined to get benefit of both. We have seen what are the advantages of sharding and how does the replication work, right? So sharding will help us to distribute the data and replication will help us to improve the availability and resilience. So by combining these two aspects into one, we can come up with sharding and replication, right? So here we have two figures. So the first figure is about using master slave replication together with sharding. So if you see this figure, each shard may have its own master here and multiple slave nodes are there which will replicate the data from master, right? So this combination will allow us to both scale horizontally, that is for the sharding purpose, sharding advantage, and next we have is to handle the replication aspect, that is heavy load. In order to handle the heavy load also, it is possible here via replication process. So master slave replication with sharding. So here each shard may have its own owner and multiple slave nodes will replicate the data from master. So this will have it will allow the combination, that is scaling horizontally and handling more traffic via replication. So here each shard might have a master node. Multiple slave nodes can replicate data from master to handle the read request. So this setup will improve the scalability with the resilience of replication. So again, both the aspects have been covered here under master slave replication. Next we have peer-to-peer replication with sharding. So peer-to-peer replication with sharding, here the data is split into shards and each data can be replicated across multiple nodes. That is, peer-to-peer connection is being established here. So this replication factor is usually taken as 3. So here replication factor means it will tell us that each shard is stored on 3 different nodes. We can say that if suppose a node fails, then the data from that node will be still available from the other nodes that have replicated the shard. We can say that this approach both for the master slave and for peer to peer. So this approach is useful when the systems require high availability and resilience. It will also help to balance the load as the data is being distributed here equally across multiple nodes. So this was about the combination of sharding and replication. Firstly we saw in the master slave replication and then we saw in peer-to-peer replication. Again, All these are very simple topics you can write directly. All next, moving further, we have second chapter. Second chapter comprises of consistency. Again, in this there are 5 topics. Let's look into them one by one. So while relational database will emphasize strong consistency by avoiding the concurrency issues, we know how concurrency issues occur. Suppose there are two users who are trying to access the same bank account. If here he is adding 100 rupees and here if he is deducting 500 rupees, and at the same time they are checking the status of their account, then the data would be inconsistent here, right? So in by making use of transaction control and concurrency control, we can encounter such issues. That happens in relational database. So relational database emphasizes strong consistency by avoiding the concurrency issues. Whereas if you are speaking of NoSQL database, it has a flexible approach. It has a more flexible approach which uses eventual consistency and allows for more complex ways to handle the conflicts. So deciding between the pessimistic and optimistic concurrency models depends on the trade-offs between the safety and liveliness. Liveliness means responsiveness. So again, consistency and the responsiveness are both important, with replication being added. So in order to address all these, we make use of the consistency aspect or the consistency model here. So the first one we have is update consistency. In exam they can ask about update consistency for 10 marks, or combinations of two types of consistencies for 10 marks. So here you'll have to describe what are the types of conflicts which will occur and what are the consistency approaches which we'll make use of. So update consistency revolves around how updates to the data store are handled. So when you update a particular entity, or when you update a particular data store, how is it handled is dealt in the update consistency, especially when multiple clients are trying to update the same data simultaneously. As I told you the example of two people trying to access the same bank account, how do we handle the consistency issues here is what is dealt in the update consistency. So suppose let's take an example where there are two users, Martin and Pramod, who both try to update a telephone number in a system at same time. Okay, so they both are trying to update the same telephone number at same time. In such condition, there will be a conflict which will occur, right? So this conflict is called as write-write conflict. So write-write conflict occurs when two users are attempting to update the same piece of data at the same time, right? So here, if Martin and Pramod both want to update the phone number with different formats, so how does it? What will happen now? So if the system applies one update before the second update, it could override the first update. Thereby, there could be lost update situation happening, right? So here the system loses the first update without the notice to the user, right? So if suppose if Pramod is here and Martin is here, and here we have the phone number. If Pramod is trying to change the number with 888 and Martin has another number 777, so if Pramod's update is quicker, then Martin's update would be lost, right? So that this condition is called as lost update will happen. In order to overcome in order to address this issue, we have consistency approaches. In this consistency approach, we have first one is pessimistic approach. In this approach, write locks are used to ensure only one user can modify the data at a time. So by making use of write locks, we can give the authority to only one user. Either Pramod can perform the write operation or Martin can perform the write operation. For example, Martin gets the lock and he applies his update. Once the update is executed, then Pramod will be forced to once Martin is editing the data or updating the data. After that, in this meanwhile, Pramod will be forced to wait until Martin completes his update. After Martin's update is completed, then only Pramod can do his operations accordingly. Then after that, he can change the data according to his wish. Next we have is optimistic approach. So in optimistic approach, conflicts are allowed, but system checks whether the data has changed since the user last read it or not. So if it has, then the second user is notified of a conflict and they can decide whether to retry or solve the data further. In this case, suppose Pramod and Martin is there, both are trying to update the telephone data. Pramod has performed one change and Martin is trying to update. Now Martin will get a update, Martin will get a message or a notification informing that Pramod had performed a change, Pramod had performed an update. Now Martin can decide Martin is notified about the conflict, right? So Martin can decide whether to retry or resolve this particular issue. So there are two techniques to handle these consistency approaches. If we are speaking about consistency in distributed systems, so in distributed systems there will be multiple nodes, right? So these multiple nodes will be handling different parts of data because the data is being split into different clusters of servers. Right. So this means that if there are two nodes which are trying to apply updates in different orders, it can again lead to inconsistencies in the data across replicas. So in order to solve this, sequential consistency is used to ensure that all nodes apply operations in the same order, keeping the data consistent. So there will be a sequential updation, sequential consistency which would be followed. So first Pramod will update, then Martin will update, then Martin's friend will update, and accordingly. Right. So by this sequence, the data would be consistent and updates will be addressed accordingly. Or a system may save both updates and mark them as conflicting. So in this condition, Martin has also given, Pramod has also given, system will save both the data and mark it as conflicting. Now the system needs to merge the conflicting changes, which can involve the user to pay attention towards it. So Pramod has also given a data and Martin has also given a data. Now the third person, maybe let's say the bank administrator or the manager or the database administrator, will have the right to look into these conflicting issues, and he'll check if this data is this data could be selected, or this data could be, or the other data could be selected, or both these data could be merged, both these conflicting situations could be merged together, overcoming the issue, overcoming the consistency issue here. So this was about the update consistency. We have spoken what update consistency is, that is write conflict, and how do we address these, by making use of either pessimistic, that is lock, write lock, or we make use of optimistic, that is sending the message or notification. Then we saw about the consistency in distributed systems. Next we have is the read consistency. So read consistency arises when a client reads the data that is in the process of being updated. So Pramod has written some change. Pramod has told x is equal to 100 and initially x was 0 here. While this operation is being still performed, Martin is reading the data. When Martin reads the data, x will show 0 only, but then actually x was being updated to 100, right? So this situation is called as the read-write conflict. So assume a situation where a shipping charge is recalculated based on the line items in a order. So here the shipping charges are being calculated, right? If one user adds a line item while another reads the line item and shipping charge, then there could be a read write conflict, because the items are being added continuously by one user, and on the other hand we are just reading the line items and then calculating the shipping charges. So in that case I might miss out the first person's line items, right? In such conditions the data might be lost, thereby read write conflict will occur. We have logical consistency. So logical consistency will make sure that different data items make sense when they are viewed together. For example, the shipping charges should reflect correct value based on all linear items. So depending on the linearity of the items which are being added, the line items, we have to calculate the shipping charges accordingly. By following this logical consistency, it will reduce these conflicts. Relational databases use the transactions to maintain logical consistency, ensuring that no one reads data while it is being updated. So by making use of the logical consistency, where we are telling during the update operation, during the write operation, reading should not be enabled. Thereby again we can maintain the consistency here. So speaking about the NoSQL databases and transactions, not all the NoSQL databases support transactions in the same way like how relational databases do. But then many NoSQL databases provide the atomic updates with an aggregate, that is consistency can still be maintained within a single entity. For example, under order entity, all the list items and shipping charge could be maintained, but not across multiple entities. Multiple entities could be the orders, or there could be the again shipping or any other thing like personal details and all of that. Right? Consistency could be maintained by while combining everything into one entity, but then when it comes to multiple entities, it is not allowed in aggregate function as we know it. Right? Conflict in logical consistency. So we know that this scenario will lead to read-write consistency. Suppose Martin is adding a line item to a order, and Pramod is trying to read the line item and the shipping charges at the same time. Well, Martin is still trying to update the charge. In this case, we can say that Pramod might see a inconsistent state, because here the shipping items are not being added, or it is not being updated. It is not being updated at the same instance, right? So by adding the line items, even the shipping charges would be updated accordingly, right? So Pramod might see inconsistent state because updation is not happened here completely. So this was about the figure 5.1, which speaks about the logical consistency. Next we have is replication consistency. So replication consistency is again a very simple topic. That is, when data is replicated across multiple nodes, when the data is replication means you are trying to store the same data among different nodes. Okay, so inconsistencies can happen between the replicas. That is, one replica may reflect the outdated value, which can again lead to replication inconsistency. Suppose let's take there are the cost is being replicated into multiple nodes here, and here it is 100, here it is 200, here is 300, 400, 500. All these data were updated as and when the cost was being changed, or cost was increasing. Now I can say that there is one replica of 100, another replica of 500. When I search for cost, these two answers will be there here. Now which one is the correct answer? So again there is a replication inconsistency which is being addressed here. So replication consistency will ensure that all nodes in the distributed system eventually agree on same value, but before they do, the data can be stale, right? That's what I told. Instead of figuring out which data is the accurate one or which data is the latest one, we will make use of replication consistencies, where all the nodes in the distributed systems will discuss, and they'll come up with, okay, for cost it has to be 100, be it you, for all they have to store the cost as 100 only. But before this replication consistencies happen, it could be 100, 200 accordingly. That is, stale data could be there. Next we have eventual consistency. Eventual consistency refers to eventual convergence of data across all the replicas. That is, if if no further updates are happening, then all replicas will eventually converge to same value. If there are no updates which are being happening, then all these can merge into one value only, right? So however, during this period, users might see different versions of data at different nodes, which is again it is natural to figure out different data which is being reflected, right? So this was about the replication consistency. Under replication consistencies, we have to write about the replication consistency, how does it encounter this issue, and what is about the eventual consistency. Example of replication inconsistency. So we have Pramod here. Pramod is trying to access a particular hotel, is trying to book a room in that hotel, and one of the hotel node is present in Mumbai, and the same nodes are present in London and Boston. Okay, so Pramod has booked the hotel here. Pramod has booked the room here completely. Okay, after that, so we can say that the nodes are being replicated to other locations. But then here, when Martin is trying to access the data, or this person is trying to access the data, they can see that the room is not booked yet, because update operation is being processed here. So in such case, we can tell that given a node, the replicas are being present here, but then these replicas have outdated values, which can lead to replication inconsistency. So thereby it is very important to address the replication inconsistency. So we make use of the eventually agreeing to the terms, or eventual consistency is being used. Next we have is relaxing consistency. So under relaxing consistency, speaking from the system design perspective, maintaining consistency is very important, but then along with maintaining the consistency, the performance costs also increase, because in order to maintain consistency, you are adding new processors, or increasing the number of nodes, or taking more time for processing. Thereby all these would contribute to increase in performance costs. So maintaining these consistency is very important because it affects the performance and availability aspect. So when we are speaking about the consistency, it might be in favor of better performance, or it might be from the availability perspective. So relaxing consistency in relational database. So we can say that even in the traditional databases, consistency sometimes relieved to improve the performance. For example, isolation levels in the SQL transaction can be adjusted to allow more concurrent at the expense of strict consistency. So here the read committed isolation level will allow some inconsistency, but performs better than the most strict levels, that is serializable. So we can say that even by let going the consistency, if we are getting more better performance, then why not? So even the relaxing of these consistency rules are also followed in the relational databases. Speaking from the NoSQL database, so in NoSQL databases, consistencies might be sacrificed entirely to get the scalability and performance. Here it was just few aspects, but here we can entirely give up the consistencies, entirely relax the consistencies to get scalability and performance aspect. For example, the distributed systems like sharded databases or systems that require the eventual consistency can handle massive amounts of data, but the updates may not be instantly visible across different nodes. That's what we have seen in the relaxing inconsistency situation, right? So here you can give relaxation to the consistency rules also if you have to maintain the scalability and performance. Speaking of the real world example, we can say that eBay and MySQL or any other similar large websites will let go the traditional database transactions to meet their performance needs. This means they sacrifice a strict consistency to ensure that their system will scale and perform efficiently when there is heavy load under them. So this was about the relaxing consistency. It is a very simple topic, very easy to write also. Moving further, we have cap theorem. So cap theorem was proposed by this person Eric Brewer in 2000. So cap theorem is a important question. It could be asked for 10 marks. You have to draw a diagram and then explain it accordingly. So cap theorem was proposed by this person Eric Brewer in 2000, and cap theorem states that in a distributed system you can only guarantee two out of the three properties. Three properties are consistency, availability, and partition tolerance. So all these three properties are the fundamental concepts in the distributed system, especially in NoSQL database. So cap theorem will tell that in a distributed system we can only achieve any two, either it could be consistency availability or availability partition, consistency partition, any of the two out of three properties at once. So we'll look into these one by one. So consistency means every read will receive most recent write. That is, every read will get the most recent write. So it will ensure that all clients view the same data at the same time. Thereby, we are maintaining the consistency. Next, we have is availability. That is, every request, be it the read request or the write request, will receive a return response regardless of system's state. So even if some nodes are down, it has to get a response back. That's what availability speaks of. Next we have is partition tolerance. That is, system must function even if there is network partition that will separate the nodes. That is, every system continues to operate despite the network partition. So partition tolerance is essential here because in the real world distributed system, network failures are inevitable. You can't avoid the network failures, right? So partition tolerance or the network tolerance are very important here. So major priority is given to these aspects. So this trade-off, the theorem entirely claims that we may experience network partitions. We must trade off between the consistency and availability. Again, they have spoken about the trade-offs between the consistency and availability. We have to select either of these two along with the partition tolerance. So that's what they have told, right? So for example, if two users are trying to book the last hotel room on separate locations or separate nodes, consistency requires that both nodes will synchronize before they confirm the booking happens. So if a partition occurs, then the systems may either sacrifice the availability, that is not allowing the booking while ensuring the consistency, or sacrifice the consistency, that is by allowing the booking on both nodes, and it will again lead to problems further. So we can have two options here. This trade-off means that in presence of network partition, we have two options. First one is ensure that all data consistent at cost of availability, that is system may refuse requirements while maintaining the consistency, or we can maintain the availability by allowing some inconsistency. That's what I told, booking multiple nodes. So I took an example to explain both these conditions. It is the same thing. Okay, so looking at the examples now. So examples of CAP theorem in practice. First one we have is consistency focus. We saw under CAP, it could be from the network partition system, either it could be CP or it could be AP or it could be combination of CP plus AP, right? So examples of CAP in practice. So consistency focused. So under consistency focus, we can look at the example of financial systems where we ensure that transactions are processed in strict order that is important than the immediate availability. So we can say that when a ATM is processing a particular request, it is very important to maintain the consistency, that is the data has to be updated accordingly, right? So it is not the user can wait up to 2 minutes, but it is very important for the transactions to happen in the strict order. That is, if a Martin is trying to change the data, or second next if other Pramod is trying to change the data, first Martin's request has to be addressed, then Pramod's request has to be addressed. We can make Pramod to wait for 10 minutes or 1 hour or accordingly until Martin's transactions have been completed. That is consistency focused. So over a network partition, consistency is given a priority in such condition. Next we have is availability focused. So speaking about the websites, for example, the news websites. So news websites cannot go off, right? So they can tolerate inconsistency. That is, they can keep on presenting the same data, the old data again and again, in order to remain available available 24 into 7. Even during the network issues, also they have to be available. So that's what availability focus. Here we are focusing on availability. Looking at the mixed approach, it is combination of both consistency and availability. So here examples are the shopping carts in Amazon's Dynamo, where we accept inconsistencies and resolve the conflicts later. There, and we also merge the items added to the cart after network partition. So here it is availability focused, and here it is consistency focused. So mixed approach is again used in order to ensure that the entire transaction of the systems are being happen or are happening properly over a given network partition. Here is the figure for the cap. So here we have consistency, availability, and partition tolerance. Either it could be CA, AP, or CP. So combinations, if we see, either it could be consistency and availability. That is, will ensure that all nodes see the same data at the same time. That is consistency, and will ensure that all requests will get a response back. That is availability. So it cannot tolerate any network partitions. We assuming that consistency and availability are met. It is pre-understood that partition tolerance is also addressed here. We cannot tolerate any network partitions here. For example, in relational databases in the centralized system. So we ensure that consistency is there, availability is there, but then partition tolerance is also has to be present here. No, there is no network partitions which we cannot tolerate such things. Next we have is availability and partition tolerance. This part. So we can say that we have to ensure that system responds to requests even during network failure. That is partition tolerance also, request should be response. We may sacrifice the consistency, meaning some nodes may have the stale data or outdated data. Example is DynamoDB, where availability is prioritized over consistency. Next we have is consistency and partition tolerance. We ensure that all nodes maintain the consistent state, that is data is being updated at once and all the nodes are trying to access the same data here, and we can tolerate network partitions but sacrifice the availability during the failures. So some requests could be denied in this case. So example here is the MongoDB, where consistency is more crucial than the availability aspect. So this was about the three combinations which we can see of CAP theorem. So again, a very easy theory topics, right? So you can easily write this. Moving on further, we have relaxing durability. So durability is a key aspect of asset properties. So durability will ensure that once a transaction is committed, it is permanent. So once I have written x is equal to 100, it is permanent, right? Even if the system crashes also, it is x will be 100 only. But in some cases, especially for the high performance systems, we may want to relax the durability for better speed and responsiveness. So this x is equal to 100 has to be compromised when we are dealing with the high performance systems in order to achieve better speed and responsiveness. That's when relaxing durability comes into picture. So examples, durability can be relaxed when dealing with the telemetric data. That is, in some cases, missing a few updates due to several server failure is acceptable if it allows for capturing the data at highest rate. So our main aim is to make sure that data is present properly and the data is being utilized, or the transaction is being completed properly. So here we can let go the durability aspect, ensuring that speed and responsiveness are met together. Right. So in some cases, missing a few updates due to server failure is acceptable if it allows for capturing data at higher rate. So that's what we have discussed. Looking at the examples of relaxing durability, first one we have is user session rate. That is, for example, in the web applications, the session losing the session state data may not be a disaster because it is temporary data, right? And the system can sacrifice this for faster response time. Next we have is telemetric data. That is, when capturing data from the physical devices, it becomes more important to collect the data quickly rather than guarantee that no data is even lost in case of crash. So here we are focusing on collection of data rather than looking at the data is lost or not. Then we have is replication failure in the master slave model. That is, if master node fails before the data is replicated, it could lead to data loss, right? So some systems trade the durability by not automatically falling over to the replica to avoid the performance degradation. Thereby we are giving let going the durability aspect here. So in all these cases we can see that system will sacrifice the durability in case of by the favor of speed and responsiveness, thereby increasing the performance, right? So the data lost could be ignored or it could be later recovered accordingly. So this was about the relaxing durability. Next we have is quorum. Quorum is again a very important topic, very simple topic. It could be asked for 5 marks. So quorum refers to minimum number of nodes which must participate in read write operation to ensure that consistency is maintained in a distributed system. So quorum helps to balance the trade-offs between the consistency and availability. So under quorums we have two types of quorums, that is write quorum and read quorum, that is depicted as W and R. Write quorum is the minimum number of nodes that must confirm a write for it to be considered successful. So the minimum number of nodes which are important, which are necessary to ensure that write operation has happened successfully, we make use of the write quorum. And speaking of the read quorum, it is minimum number of nodes we must contact to ensure that that it has got the recent data. So we are checking here the minimum number of nodes, which will tell us that it has got the latest data, and thereby we can get confirmation that okay, whatever update I had performed is being replicated accordingly. That's what we can get to know by making use of the read quorum. So we have a replication factor here which is depicted with n. So this n will tell us the total number of copies or the nodes, number of nodes which are present where the data is replicated. Next we have strong consistency. So and in order to achieve the strong consistency, it is achieved when we write, when we make use of a write quorum and a read quorum, both are met, ensuring that the data you read is the most up to date data. So we are making sure that data reading is happening successfully and the data which I am reading is the latest data or recent data. Thereby we can say that strong consistency is addressed here. Suppose write quorum example, if we see system has 3 nodes, that is replication factor here is n is equal to 3. So if I take if w is equal to 2, the write quorum, we will need at least 2 nodes to acknowledge a write to ensure that consistency is met here. For if I take r is equal to 2, the read quorum, I have to contact at least 2 nodes to make sure that whatever data they have got is the latest data or not. By looking at these two conditions, we have an inequality which is generated, that is r plus w should be greater than n, that is combination of, that is number of nodes contacted for the read operation or read quorum and a write quorum must be greater than the total number of nodes which are present in the system. So that's when this inequality is satisfied. Okay. In case of master slave model, the system will avoid conflict by ensuring that all writes will go to the master node. So master node is handling the write operations here. So by doing this, it will reduce the need for complex quorum calculations. And along with that, because master can handle writes while slaves can only process the read operations accordingly. Speaking of the trade-offs and flexibility, we have fast reads. So we might relax the consistency by requiring fewer nodes to participate in the read. So thereby it will increase the speed, but then there would be stale data. It could lead to stale data accumulation. Speaking of the strong consistency in master slave situation, we might enforce strict rules requiring all nodes to acknowledge a write condition. That is, W is equal to N is a condition here. This will slow down the write, but it will ensure the consistency is achieved. Speaking about the flexibility in operations, systems can adjust the quorums based on different types of operations which are performed. For example, if I am dealing about a high availability use case, then the system may tolerate stale data. That is, it will allow for fewer nodes in the read quorum. If I am dealing with strong consistency, it might require more nodes in the write and read quorums. So it is contrast to the above condition which we saw, right? Fast reads and strong consistency. We have only two topics. First topic is business and system transactions. Then we have vector stamps for multiple nodes. Only two topics. First topic will look business and system transactions. That is, when we are speaking from the business perspective, business processes, the concept of supporting the update consistencies in the systems without relying on traditional database concepts are very important. Business transactions like browsing products, purchases, payment transactions need more time, because here firstly you will enter your card number, then you have to enter the pin, then there will be a OTP, then there could be a captcha to verify, and all these operations are taking more time, right, compared to the normal transactions. In case of traditional databases, elements would get logged after some time, so this is impractical, right? So here instead systems can start the actual system transaction only when finalizing the interaction. By doing so, we can minimize the time database logs that are held. But then the challenges can arise when the decision like pricing or shipping are based on the outdated data that may have changed. Because the list items are being added, the pricing can change, right? So instead of locking this, if you are locking this, it could lead to problem, right? So this leads to risk of inconsistencies in the final transaction. So again, this could lead to the inconsistencies when we are dealing about the business transactions. Speaking about the system transactions, these are the actual database transactions that will ensure consistency, isolation, atomicity within a database during the business transaction. So in many cases, system transaction cannot be held open during the entire duration of business transactions. That is, because users can take large breaks, right, when they leave the computer to fetch the credit card or wait for the OTP in their mobile. So all such conditions can happen, right? So during which the database system will have to maintain the logs and state consistency, which can again be impractical or inefficient. So in order to handle these, we make use of handling concurrency with full transactions. So to handle the concurrency in such situations, offline concurrency and optimistic locking techniques are employed. First we have is optimistic offline lock. So this approach is a form of conditional update in which we ensure the data user interacts with hasn't been changed by another person. So if person A is trying to access the data, then we have to make sure that the data has not been changed by the other person after it was read, but before it was updated. So before the data is being updated or after it has been changed, the data should not be changed, right? So this can make sure this can avoid any conflicts which are happening. Next we have is version stamps. Version stamps are the metadata which are associated with a record that changes with every update. So this record will keep a track of the data. Okay. So along with every update, this data would also, this version stamp or this metadata would also vary. Okay, so when client reads the data, it records in the version stamp. So before updating it, it will check if the version stamp has been changed or not. So checking if we are ensuring that the update is made only if the data is current data, right? So next we have methods of implementing version stamps. So there are these are the typical methods which are used to implement the version stamps. First one we have is counter. So each time a resource is updated, each time a data is updated, its version number is also incremented. That's when we make use of counter. If it is 1 here, the time it gets updated, it becomes 1 plus counter. So it becomes 2. Again, if it's updated, it becomes 3, and so on. So by making use of version stamps, we can get to know that so many updates have been done. So the client will save this version number, and when he's trying to update the resource, he'll check if the version number has changed or not. So if it has changed, then we can say that update has been done successfully. If it has not happened, then we can say that update is being rejected here. Next we have is GUIDs, that is globally unique identifier. So globally unique identifier are large random numbers that will uniquely identify a particular resource or a particular data. So this will ensure that there are no duplicate version stamps, and they can't be easily shown to a new person. That is, a third person may not be able to understand these version stamps or these updated GUIDs also. Okay, next we have is the content hashes. So a hash of the resources data is used to uniquely identify the version of resource. So this is a deterministic, that is, the same resource always generates the same hash, but it will have some drawback as GUIDs. The drawback here, the drawback for GUID and for the content hash is that they cannot be used for tracking the sequence of changes, or they cannot be used to track the order of updates. That is the drawback under these two. Next we have is timestamps. So each update includes a timestamp indicating the time when it was made. So this can cause issues if the system's clock are not synchronized accordingly, and multiple updates can happen in the same timestamp window. Thereby again there could be problems, right? So some systems can use the combination. For example, counters and the content hashes could be used together for more robust conflict detection. For example, the couch database uses this approach, enabling the system to track both the recentness, that is when it was latestly updated, and and also deal with the conflicts in the distributed environment. Version stamps also help to prevent the update conflicts, but also to ensure the session consistency. So here we are checking at the prevention of update conflicts and maintaining the consistency both. Next we have is the concept of vector stamps on multiple nodes. That is, in peer-to-peer distributed systems where data is stored across multiple nodes, the version stamping mechanism is very important to handle the cases where data may be updated on different nodes at different situations. Because there is no single control over the versioning, this adds to the complexity again. For the same data, two nodes might be able to give two answers when they are queried. So this difference is happening because of the replication tag. That is, one node has received an update and the other node has not received the update, replication condition. Then we have inconsistent updates. That is, both updates have processed the conflicting updates independently, leading to diverging versions of the same data. This might say 3.4, this might say 3.5. That is, difference is being shown by two nodes when I'm trying to access the same node, one node, right? So what is the simple approach? That is simple replication scenario by making use of counters. So a simple versioning mechanism comprises of the counters, where we make use of the counter based version stamps, where each node is incremented whenever it gets updated. So each node is getting updated, the counter value will also get updated. For example, if one node provides a version stamp of 4 and another node provides a version stamp of 3, then we can go up with the fourth number, right? Fourth version, because it will tell us that it is most recent one, right? However, this approach breaks down into the multi-master or peer-to-peer models, where there is no single authoritative source to update the management, and it can lead to conflicts and complexity issues. In order to overcome, or in order to address these, we make use of vector stamps. So vector stamps are a more advanced mechanisms which are used to handle versioning in the distributed systems. So here it is collection of the counters, one for each node in the system. So they are called as vector clocks or vector version vectors, which are used to track the version for each node in the system, allowing them to handle complex scenarios. So here we can encounter, or we can handle the complex scenarios by making use of vector stamps. For example, there are three nodes, blue, green, black, and the version stamps have been specified. Blue is 43, green is 54, and black is 12. So each time a node is updated, it increments own counter. For example, if green is updated from 54, it will become to 55. So now when nodes communicate with each other, they synchronize their version stamps. So these nodes are checking which is the latest data, and thereby they'll select this version stamp, right? So this way it is possible to detect which version is newer version. So if one version has all counters greater than or equal to another version, we can say that it is a newer version. Here it is a newer version. So we'll select this. Next we have is detecting any conflicts if occurred. So if stamps have conflicts, or if the stamps have counters that are both higher than the other in the different positions, we can say that there is right conflict which has occurred. For example, if blue is 1, green is 2 and black is 5, and here blue is 2, green is 1 and black is 5. This will indicate that both green and blue nodes have updated the data independently, because thereby it has led to conflict now. So again, we can detect the conflicts by making use of version stamps. Next we have is handle the missing values by allocating as 0. Suppose if we have missing values or invalidating the existing values, we can substitute 0 there. So thereby we can overcome the drawback here. So trade-offs in using the vector stamps. Here we can tell that while vector stamps help detect the inconsistencies, they do not resolve them. They do not resolve them completely. Okay. The actual resolution depends on the application's domain logic, and it's part of larger consistency versus latency trade-offs in the inherent